So now that we have computed the spectrum of the JZ operator, let us compute the spectrum of the J squared operator. Now see that, J squared commutes with all the J's. So it commutes with JX. It commutes with, say, JY. It commutes, sorry, squared. It commutes with JZ. And therefore, it also commutes with J plus and J minus. So that means that if I find the eigenvalue of, say, psi m, and suppose this eigenvalue is something, let's call it, say, A, then this eigenvalue A will be the J squared eigenvalue of all the psi m in the multiplet, in the Hilbert space that we have derived. And that's because if you apply J plus, J minus on it and increase its m eigenvalue, because J plus and J minus commutes with J squared, that's not going to change the A eigenvalue. So that means that I only need to choose one guy from this whole set and measure its J squared eigenvalue, and it'll be the same eigenvalue for all the other states, all the other eigenfunctions. So to see this, to do this, observe that, J squared is JX squared plus JY squared and JZ squared. And then what we're going to do is that we are going to use the fact that J plus 1 plus minus are JX plus minus I of JY. Now we can invert this relationship very easily, and we find that Jx is half of J plus plus J minus, and Jy is 1 plus 2I, J plus minus J minus. So what we can do is that we can use these expressions to eliminate Jx and Jy from this relationship, and what we find is J squared is going to be given by J plus J minus plus Jz squared minus Jz. Now, if I apply it to, say, psi of minus L, then what do I get? Well, let's calculate this. J plus J minus plus Jz squared plus, minus Jz acting on psi minus L. Now, this thing acting on this is just going to give me 0. And this guy acting on this will give me minus L squared. And this thing will give me minus L. So in other words, I get L squared plus L. So, and of course, this is multiplied by psi of minus L. So this is psi of minus L. And therefore, I get L times L plus 1. So the J squared eigenvalue is L plus 1. So I can label my multiplet by the Jz eigenvalue and the J squared eigenvalue, but I can just use L. So this is J squared. Of course, J squared eigenvalue is L times L plus 1, but we don't need to write the whole thing. If you know L, we can figure out what L plus 1 is. So several comments are in order, and the first comment is that the maximum value of M, which is given by L, so L is the maximum value, so this is the angular momentum or spin of the system. This is the spin or angular momentum of the system. The other values of M, so the other values of M just label the z component of the spin or angular momentum. So in some sense, L gives you the total angular momentum, and the m value just gives you one component of the angular momentum. So the next comment is that when we know the jz value, so it doesn't make sense for us to talk about, say, the jx and the jy value. These guys don't make sense. So here's the cartoon picture. So the cartoon picture is something like, we know the total angular momentum, which is the length of this vector, and we can know the z component of the angular momentum, which is whether the angular momentum is on this plane or on this cone or on this cone or on this cone or this cone. But we don't know anything about the Lx and the Ly value of the angular momentum, and that's why all we know is that the angular momentum is on this cone. So another comment, which is a very important comment, is that the spin eigenvalues can be both integer and half integer. Whereas, so the spin is s, whereas the orbital angular momentum value can only be integer. This is not something I'm going to prove, but this can be shown. So, so number 4 is that, so given that the j squared value is L, which means that we can have two L plus 1 distinct states corresponding to the jz eigenvalue. So for example, if L is half, then we can have, say, spin half for jz or minus spin half.